לכם, אנחנו נעדכן, אבל אם לא יגיעו מי שאמרו שיגיעו, יכול להיות שאת השיעור הבא היה כמו שכתבנו. אז תעזרו בשנה שעברה, מעט אנשים שעבורם אנחנו עושים את זה באנגלית ושבאתי אם הם הגיעו אולי. יעזרו בספר, אנחנו נעדכן על זה, אבל וגם, כאילו זה לא פייר שאני אומרת את זה לכם, כי אתם בעצם מגיעים, אבל אני מקווה שיש הבנה לזה, לצפות שיגיעו 10 אנשים זה ציפייה ל10% נוכחות. אני מתאמצת בשביל להגיע, זה לא קל לי, אני מגיעה מרחוק. זהו, מבחינתי הטבלה הזו היא מהווה איזושהי התחייבות, ואם אין עמידה בהתחייבות הזו, אז נצטרך לחשוב מה אנחנו עושים עם זה. פשוט זה עניין של כבוד הדדי, זה לא כך ראוי שמגיעים פחות מ10 אנשים בשלב הזה של הקורס, שכולם מתמודדים עם אותה מציאות מורכבת, ולכולם זה קשה להמשיך את הסמסטר הזה כל כך רחוק לתוך הקיץ. בסדר?
אני חושב שכולם מתמודדים איתו, אבל באותה צורה. כאילו,
כן, יכול להיות.
כל אחד זה פוגש אותו במקום אחר, מי שיכול להגיע, מגיע, ומי שלא יכול.
אני לא חושבת אבל ש90%, זאת אומרת, יש הרבה קורסים בסמסטר הזה עם חובת נוכחות. אני לא בחרתי בבחירה הזו כי אני מבינה שזה מכל מיני סיבות, אבל 10% נוכחות, מה זה?
אני לא חושב שיש הרבה קורסים.
אני יכולה למנות לך לפחות כמה קורסים גדולים עם חובת נוכחות, כי פשוט
אני בכל התואר לא היה לי קורס עם חובת נוכחות.
כן, אבל בסמסטר הזה גלים עם חובת נוכחות, הקורס של סטס עם כאילו... בסדר, אני לא בחרתי בזה.
כשאין מבחן, אז כאילו יש חובת נוכחות אולי, כאילו... בסוף יש דרך לתת את הציון. הסמסטר הזה הוא כאילו מורכב, קשה לכולם. גם היו, לדעתי, 3 שורה שלמה ביום שני.
10% אנשים בכיתה.
יש חפיפה לחלק מהאנשים. זה יותר מורכב מכאילו...
אני מבינה, ואנחנו לא מדברים על חובת נוכחות, בסדר? לדרוש שיגיעו פיזית 10 אנשים כשהמרצה מתאמץ להגיע וגם לא עולה, זה לא קל, זה רחוק מאוד מלדרוש חובת נוכחות, זה 10%. כן. I'm talking about the fact that the requirement for 10 people to attend so that we attend too, okay? We are very far from requesting full attendance. 10% is...
I think we have 10 people now. We have 10 people now.
Yes, we might have 10 people.
And then Ahmed makes it 11, so everyone did come.
No, I'm not talking about specifically about the 10 people. I'm explaining you the rationale of this requirement. Okay, we're very far from requesting full attendance. לא על זה מדובר, בסדר? טוב. Okay, so today we're going to talk about electromagnetic waves. So we spent the last few lectures talking about the static situation, okay, both in terms of the electric field and magnetic field. And today we are finally moving to one of our big chapters, which is electromagnetic waves. Okay. Okay, and I will start with refreshing what you should know already about waves. So, who did you do the waves course with? Michael. All of you? Okay, so I can't remember if it was 1 year or 2 years ago, but we had students who had done the wave course with like 3 different people. So I'm going to spend a few minutes now reminding ourselves some basic things about waves, maybe from a slightly different perspective than what you already did, so that we all agree, okay? We all have common basic assumptions of what we mean by a wave, what we mean by a wave function, etc. Okay? Because we're going to use it in the lecture, so reminders. Waves. refreshing, okay? And I will start by reminding you the Maxwell equation for the 10th time. Okay, so let's remark, because we will also use it extensively during this lecture. So at the end, you will know it by heart. What of E? Okay, so you tell me. Yes.
dv is
0.
minus a time derivative of b.
Yes. And
It's mu 0 j plus mu 0 epsilon 0.
okay, very good. And I remind you that this and the gravity equations, which I will also use, they summarize all our sensitive experience of the world, okay? It's true that we also have two more interactions at the level of the atom, but at the end, these two equations and this one, okay, it summarize all our experience, our macroscopic experience of the world. Okay, so I'm going to start with these reminders, and here again, if I'm only saying things that you already know, enjoy it, okay? This is a good opportunity to refresh things. Okay, so let's start with the most basic questions. What is a wave?
הפרעה, מתפשטת הזמן במרחב.
Okay, so I'm hearing a perturbation, okay, which propagates, which spreads. Okay, anything else?
It's really
Which way?
It's any function of space and time that is defined, that can be, when it's put into a Fourier transform for the space, it can be defined by a dispersion relation.
Okay. Yeah, I would expect a more intuitive definition, but okay, Itai is suggesting a more mathematical definition. We will also talk about this.
So in solid state, half of it is just dispersion relations.
Okay, so I heard disturbance or perturbation, propagating, and I heard a function of space and time, okay? Okay, so I will give you a definition that contains some of the things you said, and immediately I will put a lot of asterisks, small stars, on each of these points, but this will be the definition that we will work with during the lecture today. Okay, so, and this is also the definition that is given in the Griffiths. I like it, it's pretty simple. So a wave is a perturbation, okay, that is propagating in a continuous medium, okay, and here I have my first asterisk because we all know that it's not always the case. For example, even in our macroscopic experience, okay? If we're thinking about, I don't know, a wave, a perturbation that propagates, you know, these small balls that each of them, like dominoes, that each of them, maybe you saw it in the laboratory. Okay, I can think of many perturbations that would propagate in a non-continuous medium, but for our purpose today, we will assume things are continuous. Okay, so the next point is that we will assume it's propagating with a fixed shape. Fixed shape. Okay, and here too I have an asterisk. Why? Because if I have absorption, okay, if I have some phenomenon of energy dissipation, of absorption, the shape will not remain the same, okay, it will attenuate with time, but we will ignore for now any absorption, okay? And the last point is at a constant velocity. And here too I have an asterisk because if I have dispersions, okay, if I have dispersion, then the velocity will depend on the wavelengths, etc., etc. Okay, so here I'm basically ignoring absorption. Okay, and here I'm ignoring dispersion. Okay, and here I'm ignoring the fact that there is no such thing as a continuous medium. Okay, so this is my first basic definition. Okay, and if I draw it, okay, let's draw such a perturbation. Okay, so I'm choosing this shape, arbitrary shape, and it's moving with the velocity v. This is the z-axis. It's moving in 1d. Okay, and this is at time equals 0. Okay, and at time equal t, okay, at some t, it will have moved with the exact same shape, okay, and the distance here will be what?
Vt.
Vt. Yes, you're okay. Okay, this is z. Okay, so if I now try to make some mathematical expression of just this very simple drawing, okay, any function of space and time which will verify the following condition, okay, where f of zt is equal to f of z minus vt at 0, okay, and I can write this at g of u, okay, where u is equal to z minus vt, okay. So any functions that verifies this will describe a wave, okay. This summarizes this very simple definition. Okay, it's some function, it's continuous here. Okay, the shape is remaining the same. This is what I'm expressing this here with this equal sign. And the velocity is constant. This is the velocity. Okay, and of course, it also works in the other direction. It can go to the other direction. So if I had a function, okay, of where the value at zt is equal to the value at z plus vt, 0, okay? This expresses the exact same idea, just it's going in the opposite direction. Okay, so all the function of space and time where the dependency is of the form of z minus vt are describing a wave. Okay, so let's give an example. I'm giving you two examples. And this goes back to what Itai suggested, that it's a function of space and time. Okay, so I'm giving you two examples, and you tell me if it describes a wave. Minus vt, okay, and sinus bz cosinus bvt cubed. Okay, does this describe a wave?
What?
Does this describe a wave? Is this okay? This okay? I'm giving you two functions here. Okay, they are both function of z and t. Okay, and I'm asking you that this is the dependency. These are the two functions. Is this a wave?
Yes.
Yes. Is this a wave?
I think no, but we would have to do a Fourier transform.
No, we don't. It's not a wave. The moment the dependency is not in z minus vt, you know it's not a wave.
Well, it could be a combination of waves.
Uh,
I mean, there's a standard.
you cannot write this as you cannot transform this dependency into this dependency.
So that's why I said like a Fourier transform. That's what I was saying. Like a standing wave. At first, you wouldn't think it's so. Like we know, but it's not propagating technically. But it is technically a wave of a standing wave.
This is not describing. There is a very simple way to check whether your dependency in space and time is of a certain shape, yes or no. Okay? The fact that you can describe any function with the sum of many progressive waves, this is another point. But this is not describing a wave. Okay? Because why? Just because the dependency in space and time is not of the form of z minus vt.
You can maybe put it in the wave equation, see if it satisfies. If yes, it's a wave.
Yes, you can. You can. This would be another condition, and we will see in a second. I will show you that.
It's enough. It's like
I will show you that these are the most general solutions of the wave equation, but it's enough at the end to check how does the space and time dependency look like. Okay? Okay. Okay, so very good. Inon, right? Mm-hmm. Okay, so Inon is bringing us to our next subject, which is the wave equations. Okay, so in the courses about waves, you saw that whenever you're talking about a wave phenomenon, at some point, sooner or later, a very well-known equation is emerging from the problem. We're doing some reminders about waves, okay? Okay, and this equation is of the following form. So, wave equation. Okay, and it's linking what? The second derivative in space, and it's linking 2 seconds derivatives in space and time. Okay, and what do I have here? Okay, 1 over the velocity. We're jumping to c. Velocity, okay. So this is the wave equation, which sooner or later will appear. So if you remember, in the case of, how do you say, string? Okay, V is T over mu, okay? Where T is the tension of the string, okay? So this equation in French, maybe you also heard it as the D'Alembert equation. The French they appropriate all the physics. So I studied it as the D'Alembert equation. But so this equation, a very important one, it will appear sooner or later when we're talking about waves. And what I will show you now is that the most general solution, of the wave equation is what? Okay, it's f of zt, where f is the sum of, I'm going to call it here h, okay? It's the sum of these two functions, h, w, okay? g, c minus vt plus h, z plus vt. Okay, and this links Inon's suggestion that, okay, that anything that describes the waves should be the solution of the wave equation. It's true, okay? This and this are the most general solution of this are these functions, the functions of this shape. Okay, and I'm going to show it now very quickly. Okay, and then we will move to to the specific case of sinusoidal functions, and this will end our reminders about waves. Okay, so let's show this statement. Okay, I'm showing now this statement. That's the most general solution of the wave equation, or just the general solution of these shapes. Okay, so we set u equal to z minus vt and w equal to z plus vt. Okay, and I will be able to do a variable change. Why? Because this is a bijection, right? If you remember, in order to change variable, I need some bijection relation, so that if I define two variables, I also define. You understand? bijection is קשר חד-חד ערכי, okay? בין ZT ל-UW, okay? Because, okay, so I have that Z is equal to U plus W divided by 2. U minus, okay. Okay, so I'm allowed to do a change of variables. So let's define this change of variables. So df over dz is going to be equal to df over du times du over dz. Okay, and this is what? This is 1. Okay, plus df over dw times dw over dz. And this 2 is 1. Okay, and in the same way I can redefine what?
Shouldn't it be 1/2? Oh, it's du to dz. Not
Yes.
dv.
Times du over dz, so this will be minus v plus df. I recommend that you do it together with me. Okay, this is equal to plus v. Okay, so this tells me that deriving as a function of z is like doing the sum of these two derivatives, and deriving as a function of t is doing the subtraction times v. Okay, and if I apply it a second time, because what I want to do is to derive it twice, okay, I can write that d2, the second derivative according to z, is equal to du plus dw du plus dw, right? Okay, so this is equal to d2 du2 plus, okay, plus 2 d2 du dw, right? Okay, and the second derivative according to t is equal to v2. You should check that you agree. Okay, plus d2 over du square minus 2 times d du dw, right? Okay, so I use this variable change in order to redefine the second derivatives. Okay, and what this means is that d2f over dz2 is equal, if I rewrite my wave equation, okay, d2f over dt2, this is equivalent, okay, and it's important, the equivalence here is important because it goes both directions, okay, so if I replace here, if I replace this with this and this with this, you see that this term will cancel, okay, you agree? if I just put this, so I'm putting this here and this here, okay? And then these cross terms will cancel.
No, that was the opposite. The minuses won't cancel because they're opposites. The second derivative.
Sorry. Yes, sorry. So these terms, the cross terms will not cancel. And shall I write it? Let's write it. It means that d2f over ddu2 plus d2f over dw2 plus the cross term. Yes, you're right. Okay, this is equal to d to the f over dw2 plus d to the f over du2 minus 2df dw. Okay, so this cancels and this cancels, okay, and I'm left with, so this is equivalent again to d to the f over du dw equals 0, okay, and this is equivalent to writing that f, okay, of uw is what? It's a sum of a function of u plus a function of w. Okay, you agree? You agree with this equivalence? Why? Because the first derivative needs to be a function of, because the first derivative, as according to you, needs to be some function of, like, let's call it k of w, okay, and same for w. Okay, you agree? So if I summarize, writing, and it's very important here, the equivalence, okay, so writing that f verifies the wave equation is strictly equivalent to writing that f of zt, if I go back to the original variable, is a sum of a function of z minus vt plus a function of z plus vt. Okay, so I don't know if we showed it in the course on waves, but this is a very important result, that the general equation of the general solution of the wave equation are of this shape, and these functions are called plane progressive waves. Okay, progressive waves. We will use them extensively when we talk about electromagnetism. Okay, and now I will focus on some specific form of these functions. Okay, I will focus on one type of plane progressive waves. Do you know if the air conditioning is working?
This one's working. That one and those I have.
Okay, so thank you. So let's focus on one particular case of plane progressive waves, sinusoidal waves. Okay. So these are a particular case. Okay, and it will also allow me to define the conventions that we will use. So these, by definitions, are functions of the shape a cosinus of k z minus vt plus 5. Okay? So if I had asked you, do these describe waves, you would have said yes. Why yes? Because the dependency in time and space is of this shape, etc. Okay, so this is a very particular case. Okay, and this is called the amplitude, if you remember. And here k is the wave number. Okay, and so the wavelengths. Do you remember the expression of the wavelengths?
It's 2 pi over k.
Right, it's 2 pi over k in absolute value, okay? Because I'm allowing here k to be negative, but lambda, I want lambda to be positive, okay? And this is the phase, okay? And if I take a snapshot of this, a snapshot of this function, okay, to feel what I mean by each of these things more intuitively. So I have something like this, okay? This is the function at a given time, okay? Let's call it 0, time equals 0. I'm taking a picture, hi Ariel. I'm taking a picture of this function. So what is lambda? Lambda is my space periodicity, okay? And the phase is here, this, let's put it like this, okay? So the phase is the separation phi divided by k is giving me the separation between 0 and the previous max, okay? I have two periodicity. I have one time periodicities, okay? I have a temporal one and a spatial one, okay? 2 pi over omega. I will remind you in a second what I mean by omega. So this omega here, if you remember what this is?
KV.
It's but like physically speaking.
Oh,
And we're calling it the...
measuring a single point, how long will it take it to return to the same state? In general, how long it takes the wave.
Right, but it's... So we give it a name and it's the angular frequency. Okay? And it's related to the temporal frequency. Okay, let's take one step back. So the frequency, which I sometimes call nu, is 1 over t. Okay, and it's related to the spatial periodicity. It's v divided by L. Okay, and here what I'm calling the angular frequency is equal to 2p nu. Okay, and it's also, like Itai said, kV. Okay, so this is a very short summary of all the very basic relations that you're supposed to have in mind when we talk about sinusoidal progressive waves. Okay, and we will adapt both in this course and generally a slightly more symmetrical way of writing this. We need some automatic way of raising whiteboard. Okay, so we will use the following notation. Fzt is equal to A cos kz, this is the convention we will use, minus omega t plus phi. Okay, and we can also write it as A cos of k om minus omega t plus phi, where the wave vector k is equal to k times a vector, a unitary vector that describes the direction of the propagation. Okay?
And that being its magnitude is v, right?
Magnitude.
Of the propagation vector.
Yes. Okay, so there are what are the two advantages of using these functions, these harmonic functions? Okay, these sinusoidal specific solutions, we call them the harmonic functions. What are the main advantages? Okay, there are two advantages. If you remember, one advantage is like purely methodological, which is the fact that I can use complex notations. Okay, you remember? So, two advantages. Okay, the first one is that I can use complex notation, and I will use it a lot. Notations, okay? And this comes from the fact that I can use the Euler definition of the exponent of I. Are you used to IT or JT?
IT.
J theta IT, okay. So f of z t is basically the real part of a exponent of I kz minus omega t plus the phase, okay? So I'm going to use a complex notation, okay, when the underlying here means I'm moving to complex notation, okay? So this is equal to a complex exponent of I kz minus omega t, where a here, complex amplitude, is a exponent of I phi. Okay, and why is it so interesting to use the complex notation? Simply because it's much easier to deal with exponents than to deal with trigonometric relations.
It gives the multiplication between a function of z and a function of t.
Right, it's much easier to multiply two exponents than to multiply two cosines, right? All the manipulation. So let's give an example. If I have two, let's say, assume I want to combine two functions, two sinusoidal waves, okay? So I have so I'm giving here an example. If I have f3, which is equal to f1 plus f2, okay? And I want to ask what will it look like? So I can write that it's the real part of f1 plus f2 in complex notation, right? And that f3 is equal to
real f1 plus real f2.
Yes. So a1 exponent kz minus omega t plus a2 exponent I kz minus omega t. Okay. So first, what I'm seeing here is that the sum of two progressive, harmonic progressive waves is itself a progressive wave, but I let you do it as an exercise. I think it might appear in the Griffiths too as an exercise, but this is going to be equal to a3 exponent of I k minus omega t, right? Where
It's not just a1 plus a2.
1 second. Okay, so what I will want to obtain here is, what I will be asking is a3 as a function of a1 and a2, and phi 3 the phase, right? Because a3 is a function of a, the complex a is a function of a of the amplitude and the phase. Okay, so I will want it also as a function of phi 1 and phi 2. Okay, and this will be very relatively easy to derive. I'm not going to do the full derivation here, but this will be relatively easy to derive with exponent. Okay, I'll write you the results and just check at home that you agree. Okay, so a3 is going to be the square root of a1 square plus a2 square plus 2a1 a2 cosinus of phi1 minus phi2. Okay, and the phase is going to be equal to minus the arc tangent of A1 sinus phi 1 plus A2 sinus phi 2 divided by A1 cosinus phi 1 plus A2 cosinus phi 2, okay? I think this is problem 9.3 in the Griffiths, okay? And these are both a few lines of calculation when using the complex notation, whereas if you were to derive this with cosinus and sinus and trigonometric relation, it would be much harder. Okay, so this is one advantage of thinking in terms of harmonic function, and what is the other advantage? This is also the other reason why harmonic functions are so important. Okay. So this is related to Itai's suggestion about doing some Fourier transform. The second advantage, or the second reason why it's important, these functions are, these specific cases are important, is that any wave can be expressed as a linear combination of sinusoidal ones. Okay? So by wave I mean solutions of the wave equations, the function of the form which we talked about. So fzt can always be written as an integral, okay, of a k exponents of I k of I kz minus omega t dk. Okay, so it's a sum over wave vectors. Okay, and k can be negative. Okay, this is a very important expression. So k is allowed to go to on the negative axis. Okay, but here again I'm talking about functions which themselves are waves. So they themselves verify this very specific dependency which we talked about. Okay, so this ends all the refreshings which I wanted to do about waves, and this should all be very familiar. It's all familiar? Yes? Good. Okay, and now what I will do is I will move to the electromagnetic case. Where is the... it's here. Okay, I do it here. Okay, so two electromagnetic waves from the Maxwell equations. Okay, so I'm now zooming on the very specific case. Everything I said so far is the very general considerations about wave phenomena across physics, and now I'm moving on the electromagnetic case. And what we're going to show is that a consequence of the Maxwell equation, you remember that in the beginning, in the first lecture, we tried to squeeze the Maxwell equations as much as we could to like extract all the different meanings that are contained in them. So I will now show that from the Maxwell equation we can derive wave equations, which will actually tell me that there is such thing as wave, electromagnetic wave. So let's write them in vacuum. Okay. In vacuum, I have that divergence of B is equal to divergence of B, 0, and divergence of E, No, but in vacuum. I mean vacuum.
Zero.
0. Okay, and rot of E is equal to minus dTB, and rot of B is equal to mu 0 epsilon 0 dTE. And if you remember, I told you that here we have this coupling, this space-time coupling between E and B, which is a necessary condition to make wave equations appear. Okay, so let's also reminding you that rot of rot is equal to what? You remember? Rot of rot is equal to the gradient of the divergence minus the Laplacian. Okay, so what shall I do to make a wave equation in E? What could I do? I want to use this, I want to use the Maxwell equations, and I want to see if I can get a wave equation for E. So I should take the what? The rot of which equation?
Rot of the...
I'll take the rot of this, right? So if I take the rot of this, I will get that rot of E, I recommend that you do it at the same time, is equal to the gradient of divergence of E minus the Laplacian of E. Okay, and this is what?
0.
This is 0 because I'm in vacuum. Okay, so this is 0, and this is also equal because of this. Okay, this is also equal to minus dt rot of B. Do you agree? You agree? I'm just taking the rot of this, and this is minus dt mu 0 epsilon 0 dt E. Okay, because of this. So I'm happy. Here I have a second derivative in space. Here I'm making a second derivative in time. Okay, this is exactly what I wanted. So Laplacian of E is equal to mu 0 epsilon 0 d to second derivative in time. Okay, and this gives me a wave function where the velocity is what? 1 over v2 is what?
Epsilon 0.
Yes, exactly. Okay, so v, okay, which is actually c 0. I'm putting a 0 here because it's the velocity in the vacuum. Okay, is equal to 1 over mu square root of mu 0 epsilon 0. Okay, and in order to get a wave equation for B, it's going to be the exact same exercise. I'm going to take rot of B. Okay, I'm taking the rot of this. Do it as an exercise because it's really the same. And I'm getting that the Laplacian of B is equal to mu 0 epsilon 0 d to B over dt. Okay, so I've showed that the Maxwell equations actually mean wave equations for E and B. Okay, so this was A, this was the proof. Now I'm going to make some, I will do 4 comments which are very important to take a step back on this. Okay, so the first comment that I want to make is that what I did here, did I do any approximation? Do you agree, Yuval? Yuval, do you all agree with Yuval? that I didn't make any approximation. The question is, did I make any approximation to get the wave equations?
You said you were in vacuum.
What?
You said that you are in vacuum, that's all.
Yes, I said I'm in vacuum and then I derived it in an exact way, right? Now I want you to try to remember the course on waves. Was it the case, for example, if I'm taking the example of a string, okay, is the wave equation for a string exact?
No.
No.
Hmm? No, it's not. Do you remember what approximations you had to do?
Constant.
You do second degree and third degree
Small
approximations.
Small angle.
Small angles,
Yeah.
actually. So we're also doing all kind of simplistic assumption about the tension, etc. But at some point, you did some small angle approximation. So I will very quickly remind you of this. Okay, so if you have, this was the string, okay, and you have some tension here and some tension here, okay, and here you had theta prime and here theta. So the way you derived this was by writing the Newton, just the Newton's law for the string. So you wrote that the variation in the force, in the transverse force, okay, in this direction, transverse force was equal to T sinus theta prime minus T sinus theta, okay? And because of small angles, and only because of small angles, okay, you could write this as a tangent. So T tangent theta, and because it's a tangent, you are able to write it as df over dz at z plus delta z minus df over dz at z, which is exactly the definition of the second derivative times delta z. So this is equal to the second derivative times delta z, okay? And this, because of Newton, was also equal to mu delta z. So this mu is the mass per unit of length. Okay, did f did z to square. Okay, no, sorry, did f d2 square. This is just Newton. Okay, and so by using these two things, you would get the wave equation. Okay, and all the other cases that you showed in the course about waves were also assuming some approximations. Was equal to f over dt2, and v was just t over mu. Okay? So the first comment is that, so b is comments. Okay, so the first comment is that the wave equations in electromagnetisms are exact in vacuum. Okay? The second comment, which maybe is obvious, but I think it's incredible, is that we have waves in vacuum. Waves, electromagnetic waves, don't need any medium to propagate. They just propagate in vacuum. We've reached these equations by assuming we're in vacuum. Again, this is also very different from any waves that you studied from mechanical cases. Okay, we don't need any medium to propagate. And the third comment, which is very related to this, so no need for any medium. At the time this was discovered, it was mind-blowing, okay? The third thing is that because this is equal to the velocity of light, this led people to realize that electromagnetic waves are light. Okay? For us, again, it's completely obvious, but at the time, it was also mind-blowing. What should there be any relation between electricity and light, right? Again, it's an obvious fact for us, but at the time it was completely mind-blowing, and shortly after this was discovered, Hertz was able to emit and detect electromagnetic waves, and this led to countless applications, radio, TV, cell phones and whatnot. But this again was a pretty mind-blowing thing at the time it was discovered. Okay, and the last comment I want to make is that, so no need for any meter. Electromagnetic waves are light. Okay, it's the same, physically speaking, it's the same phenomenon. Okay, this is mind-blowing. Okay, and the last comment is that I wrote 2 wave equations, but we actually have, for each of these wave equations, we actually have 3, right? We can write a wave equation, because this is a vector Laplacian. Okay, so I can actually write 1 wave equation in each of the coordinates. You agree? So we actually have 3 wave equations. For E and B, right? I can write, for example, the following: d to t x. Okay, I have 1 wave equations for each of the components of the field. You agree? If you just write this wave equation on one direction, it gives you 3 wave equations. I actually have 6 wave equations in electromagnetism. Okay, now what I want to ask in the rest of the time before the break, now I'd like to ask the following questions. We showed that we have wave equations for the fields, right? And the question I want to ask is, do I have wave equations for the potentials? Okay, so the electromagnetic field can be described as a wave in vacuum. Can I describe the potential, both the vector potential and the scalar potential? Can I write them as waves too? Do you have a sense for the answer?
Intuitively, I think it should be correct.
Okay,
Because,
I agree with you. Yes, because if I have a wave in E, right? That should be okay. And
periodic, if we think of like a periodic wave, then
yes, I agree with you. So Inon is saying intuitively, I should be able to write some wave equation for the equations for the potential, because these are very related quantities, and if one is propagating as a wave, why the related quantity shouldn't be? Okay, and this is correct, but the answer is that mathematically I will have to put a constraint on the potential in order to get wave equations. And I will be able to put this constraint. Why? Maybe you remember we spoke about the Coulomb fixing, the Coulomb gauge, where I told you that V is defined up to what? Sorry, A is defined up to what? To a gradient. You remember we said this? That the vector potential, I have some freedom to define the vector potential. This freedom is what? Is the gradient of a scalar function. Okay, and the Coulomb gauge, the Coulomb fixing, was some constraint that I required. If you remember the Coulomb gauge, it's writing that divergence of A is equal to 0. You remember this? So this constraint was something I could, a decision I could make because I had such a freedom in A's, because it's defined up to a gradient. So here I will show you that in the exact same way there is a constraint that I need to impose on the potential to be able to write a wave in the potential. I cannot write a wave function just for any vector potential. There is a specific constraint I need to add, and I will show you that this constraint is exactly the Coulomb gauge in the limit of stationary cases. Okay? Because the Coulomb gauge, if you remember, was derived within the stationary context. Okay, so let's do it. So 3 will be wave equations for the potentials. Okay, so 3 will be wave equations for V and A. Okay, and the underlying question is, I'm asking what do I need to require to request so that potentials too are waves. Okay. Okay. So a quick reminder of what we're talking about, of the of the potentials. Okay. So for each mt in time and space, there exist two functions. There exists a function A such as B is equal to rot of A, and there exists a function E such as E is equal to minus grad V minus dA over dt, and we saw that V is defined up to a constant, okay, and this is why many times in exercise we have the freedom to request that V will be 0 at infinity, right? And A is defined up to a gradient. Okay. Okay, so A is defined up to a grad of F. Why? Because rot of something plus a gradient will be rot of this something, because rot of grad is 0. Okay, and so there was something that we called the Coulomb gauge, okay, which was basically requesting that divergence of A will be equal to 0. Okay, and why do I know? How do I know that I will always be able to do such a request? Okay, let's assume. Okay, so if we assume that divergence of A is not equal to 0, I can show you that I will always be able to define A prime such as the divergence will be 0 and rot of A prime will be B. Okay, so let's quickly show it. Okay, so if I have that A prime is equal to A plus the gradient of a function f, okay, and divergence of A prime is equal to divergence of A plus Laplacian, because div of grad is Laplacian, right? This is divergence of A prime. Now, I'm assuming that the divergence of A is not 0 and divergence of A prime is 0. Okay, and this, if this is non-zero, okay, this is exactly like writing that df is equal to a scalar. Okay, and what is this equation? This is the Poisson equation. And the Poisson equation, we know it has solutions, right? So even if I had that divergence of A is not 0, there will exist some solutions, A prime, so that divergence of A prime will be 0. Okay? So this is telling me that I will always be able to do such, to impose such a requirement. Okay? This is what we call the Coulomb gauge. Okay? Or in Hebrew it's חופש הכיול של הפוטנציאל הוקטורי. Okay? So this was the Coulomb case. And now we're going to define a slightly different gauge, a slightly different Q, okay, that will allow me to get wave equations for the potential. Just check. Okay. Okay, so so let's write the following. So for every mt, I have that rot of B is equal to rot of A, right? And this is equal to mu 0 epsilon E0 dE over dt, okay? Which is equal to minus 1 over C0 square of d over dt grad V minus 1 over C0 square d to A over dt square. Okay, this is just from the definition of the potentials. Okay, and this implies, okay, so this, I'm using the usual vector identity, so grad of divergence of A minus Laplacian of A is equal to minus grad, I'm taking the grad out here, okay, of 1 over C0 square dV over dt minus 1 over C0 square d to A over dt2. Okay, and this implies that Laplacian of A minus 1 over C0 square d to A over dt2 is equal to the gradient of divergence of A plus 1 over C0 square dV over dt. Okay? So this is just from writing the definition of the potentials. Okay? And you see that here this part is the part I will be interested in to get a wave equation, right? You agree? Yuval? בסדר? Okay, so if I want a wave equations to appear here, what do I need? What is the condition so that this turns into a wave equation in A? Okay, I remind you that the question I'm asking here is, what do I need? What conditions do I need to impose on A in order to have a wave in potentials, in vector potentials? Okay, and here I have something that looks very much like what I want for a wave equation. So what do I need to impose so that I get a wave equation in A?
Maybe the right side needs to be 0.
Right, so this needs to be 0, okay, and this means, and this is a spatial derivative, right? So this means that I need this to be some function of time. Could be a constant too, but it's enough that it's a function of time, you agree? Because then the spatial derivative will be 0, and I will get a wave equation in A, okay? So if for every time in space and every point in space and time, I have that the divergence of A plus 1 over C0 square dV over dt is equal to a function of t, this will imply that I have a wave equations for the vector potential. Okay. dt2 is equal to 0. Okay, now this was a condition to get a wave equation on A, on the vector potential, but I also want the wave equations to be verified for V. Okay, so let's do the same exercise and ask, will this condition be enough to ensure that I also have a wave equation in V? Okay, so let's ask this. Okay. Okay, and I'm going to do something similar. I'm going to write that for each mt, div of E is equal to 0. Okay, and this is equal to minus the Laplacian of V. Why? Because this is equal to minus grad V minus did A over dt. Okay, so I'm taking the divergence of this. Okay, so this gives me the Laplacian. Okay, minus the divergence of did A over dt. And this is equal to minus the Laplacian minus d to dt, divergence of A. Okay, but this divergence of A, I can use this condition I already have, right? Divergence of A is equal, so if I write it again, this is equal to minus the Laplacian of V minus d to dt f of t minus 1 over c0 square dv to dt, right? Here I'm just using this. Okay? So this means that for every mt, I have that Laplacian of V minus 1 over c0 square d to dv over dt 2 is equal to df of t over dt. You agree? And here again, what I have is that in order to make this a wave equation in V, I need this to be 0. Okay? So if I summarize both things, okay, in order to, so let's write it. So df over dt equals 0 for every m and t will mean that I have
a constant.
wave equation in A, and this will mean that I have a wave equation in V. Okay? Wave equation. Okay, so I need f to be a constant. I can request it to be 0 because then it will also ensure that the potentials at infinity will be 0. So if I summarize both conditions, okay, if I summarize both conditions, if for every mt I have that divergence of A plus 1 over C0 squared dv to dt equals 0, this will mean two wave equations. Okay, one wave equation in A minus 1 C0 squared d to A over dt2 is equal to 0. And this is a vector equation, and this is scalar one. Okay? So, and this gives me the answer of what I need to require in order to have waves in potential. Okay, and you see that in the limit of stationary cases, this goes to 0. Okay? Now, case. This goes to 0, and I'm back to the previous, to the Coulomb gauge. Okay, this is called the Lorentz fixing or Lorentz gauge. Okay, and this is exactly the previous requirement I had in the stationary case for A. Okay.
Could we maybe have that for t is not equal to 0?
Yes, it can be a constant.
Even a function of t, because
but it needs, so f needs to be a function of t and not space. This is to ensure that I have waves in A, right? But then, in order to also have waves in V, I need the derivative of the temporal derivative of f to be 0.
But I think we saw in waves that you can have a forcing term, I think it's called.
A what? A forcing term?
Yes, you can have the Laplacian minus the second time derivative not equal to 0. It's still a wave equation with the wave solutions. No?
כוח מאלץ כאילו.
כן, אבל physically speaking, it's a different, it's a slightly different question. So I'm not, right, I can, so if I have this, it's a slightly different problem. You will have some waves and they will align with the forcing terms, etc. But here what I'm asking is, I don't have any forcing, like in vacuum, I don't have any forcing term, okay? And what I'm asking is, do I have spontaneous waves that develop in vacuum? It's a slightly different physical question. You're right, but it's a different problem and it's a different equation. Here I'm asking, do I have spontaneous waves? I don't need to force.
Because we were looking for the most general conditions in which we get waves, like the
in potential.
Yes.
But the same kind of waves.
Conditions we need to have wave solutions for A and V, and even if f is not constant, if it is a function of t, we still get waves.
Yes,
so
but we're not so. Okay, so but again, it's a different the way. it's like asking if I have a string, I'm doing this on one side and leaving it to go, will it propagate? Or if I continue to do this, what will happen? Okay, this is the meaning of the forcing term. If I continue to impose something, it's not a wave in the term of one perturbation that is propagating no matter what. Okay, so again, it's a different, and what I'm asking for the potential is the physical question in the same sense that I'm asking for the field. Like, if I have a perturbation, is it propagating like a wave? Okay. Yes.
Do you can get a wave equation for A and V for each dimension?
Yes, if I'm doing this request, and it sounds like I'm imposing something, but you can also understand it in a different way. You can understand it by saying there is an infinite number of vectors A which verify rot of B equal A, okay? And of all this infinity of functions, the ones that behave like waves are the ones that verify this function, this condition. Okay, and the answer is yes. So this actually translates into 3 wave equations for each of the components of A, okay, for AX, AY, AZ. And this is a scalar equation, so just for V. Okay, does it answer your question? Mm-hmm. Good. Okay, so just to summarize, we made some refreshing reminders about waves. We showed that from the Maxwell equation we get electromagnetic waves, and we also we made some comments, important comments on these waves, that they are different in essence from all the waves that the mechanical waves that we are familiar with, and they're also light. Okay, or they put scientists in the direction of understanding that, including Einstein, okay, that light and electromagnetisms are basically the same, intrinsically the same phenomena in essence. And then we said, okay, there are waves in fields, there should be waves in potential, and this is actually true, but not for any potential, just for the very specific potential that verifies this condition. Okay, this is a summary of everything we did in the last hour and a half. And after the break, we'll talk about what we can understand about the shape of these waves from the Maxwell, the structure of these waves in the vacuum from the Maxwell equation. Now, by the way, I will need you to show me exactly what you mean from your lectures on waves, because I thought about it in the break and I'm not sure I understand what you meant. Because the waves as we define them are this specific set of functions which verify the wave function as we define it. So it's a different equation. I'm not sure we're talking about the same thing.
I think it's just that the same functions, they satisfy also that equation. But I can...
Yes, you can show me. It's an interesting question. Okay, so now what I will try to do is, as part of my advocating of the Maxwell equation as the sources of all knowledge in electromagnetics, we will try to see what we can learn about the structure of the electromagnetic waves from the Maxwell equations. And here I will ask you what do you remember? What do you remember from the structure of the wave? So by structure I mean the directions of E, the direction of B. What do you remember about this?
They are orthogonal.
Okay, so E and B are orthogonal. Always or only in vacuum?
Always, I think. And they're also orthogonal to the direction of travel.
Always or only in vacuum? Both B and E? Structure of electromagnetic waves. Okay, so Ariel is saying B and E are orthogonal, and they are orthogonal to the direction of the propagation. It's almost true. Okay, so I will remind you what we know, and then we will derive this from the Maxwell equation. Okay, so I'll remind you what we are supposed to know from previous lectures. Okay, so the first thing is that okay, B, E, and EZ, they form a trihedron, okay, like this, and their mutual directions are defined by the rule of the right hand, okay? So, direct trihedron. So this means the right hand rule, okay, and this means that I have, okay, this is the mutual directions, but I'm not implying here necessarily orthogonality. I will talk about it in a minute. So if this is EZ, okay, so B, E, EZ, right? So it's B, E, EZ. Okay? So this is one thing. Okay, so it means that I have some polarization too. The fact that it's the right-hand rule. It's not just any orientation. Okay, it's there is such thing as polarization, not in the sense that we talked about before of polarizing material, but in the sense of some specific. I don't know if you heard about polarimetry and things like this. Polarization, it can also mean the fact that E and B have a specific direction, and if you have polarized sunglasses, this is also what's implied, okay? Okay, so this is one thing. So B is always perpendicular to the direction of the propagation, okay? B is always perpendicular to E, okay? And E is perpendicular to the direction of the propagation when only in vacuum, okay? In a second I will rederive this, but these are the things that you must have in mind, fresh in mind when you imagine and think about the electromagnetic wave. Only in vacuum, okay? And the last thing is that there is a connection between the value of E and the value of B, if you remember, the norm. Okay, I'm also including this in what I mean by the structure of the wave, okay? At any given moment, there is a relation between the value of vector E and the value of vector B. Do you remember this relation? No? I will remind it. So, okay, so for any it means that you can deduce the value of E from the value of B, okay? They are linked. So for any T and any Z, the value of E, okay, is related to the value of B through this relation. Okay, so there is a factor C0. And if I summarize all these things, I can write it in a more compact way. I can write that E plus C0 EZ cross B is equal to 0. Okay, so this is a very important relation which summarizes actually all these things. Okay, if they are equal to 0, if the sum is equal to 0, these three vectors need to be orthogonal. Okay, so this summarizes it. Okay, now, sorry, and this of course is in vacuum. Okay, where C0 is of course 1 over square root of mu 0 is 0. Okay, so now it was like a reminder of what you should have in mind. Then let's show it. And there are several ways to show it. There is one way that uses specifically harmonic electromagnetic waves, and I would like to avoid using this because I want to show it in the more general cases. Okay, so I will show it in the general way, in the general case of plane progressive wave. Okay, so which are these function f and g that I defined before, and I'm not using the harmonic specific case that I defined. Okay, I hope it explains why I spent so much time on the progressive function than the specific case. Okay, because now I want to use these very same functions to show this. So I'm going to show it in the general case. Case of plane progressive wave, okay, not harmonic, and I will give you the most ingredients to show it with harmonic functions, and you can do it at home. Okay. Okay. So we're back to our function f and g. And if you remember, I defined dt as what? As minus c d over dw. Okay, you can, so I'm talking about function of this form, z minus ct, and this was w. Okay, so this is a...
wasn't that u?
Maybe w was with a plus?
Yeah, w was.
Okay, so we can call it u. Okay. Okay, so here I have u, and then grad is equal to d over du ez. Okay, and dz is equal to d over, actually here, these are not partial, these are full derivative, okay? Dt. Okay, so these were the way that I go from one deriving in one variable and the other. Okay? Okay, and now I'm writing the Maxwell equation in vacuum. So rho of b is equal to mu 0 epsilon 0 dtd. Okay, and this is also equal to grad cos b. Okay, and now I'm going to translate this into the, okay, this is the first time that I'm injecting plane progressive waves in the Maxwell equations. Okay, so I'm kind of linking now the first two parts of the previous what we did before the break. Okay, so I'm injecting here inside the Maxwell equation some function of this shape. Okay, so this is going to be given by dz ez cross b. Okay, which is equal, I'm using here dz, this is d over du of ez cross b. Check that you agree. Okay, and this is 1 over c squared of dtd. this is just again using the Maxwell equation, okay? Which is also, if I'm injecting here this function, it's also going to be equal to 1 over c squared minus c d over du of e. Okay? So, if I summarize, I get that d over du of ez cross b plus 1 over c e is equal to 0. Okay, do you agree? Because I'm just bringing this term to the other side of the equal sign, okay, and I'm getting this. Okay, so in other terms, d over du of c ez cross b plus e is equal to 0. Okay, which means, so I can say that this means that this thing is constant. Okay, but one thing that is important to realize is that what I want to look at now is the varying parts of the fields. Okay, when I think about electromagnetic waves, okay, I'm not thinking. I can always define a wave up to a constant, okay, but the thing that is varying, that is oscillating, is the varying part, okay? So I'm not saying that this could not be equal to a constant, but I'm interested only in the varying part, not the constant part, okay? And this is why this will imply that C ez cross B plus E is equal to 0, and this is what I wanted to show here, okay? So, if I summarize what I did, okay, what did I use? What are the ingredients that I used? I used the Maxwell equations, okay, and I used the definition of a plane progressive waves, which is basically the general solution of the wave function, not specifically electromagnetic fields, okay? This is from the first half hour of the lecture, okay? So I used these two things, and these two things led to this relation that tells me how do E and B vary over time, one according to the other. Okay? Make sense? Okay. So I want to show you, this is all a bit not the most concrete thing. I will give you just the ingredient to do this demonstration with harmonic functions, okay, and you can do it at home. And then, because this is all a bit abstract, I will show you a very small movie that shows you E and B over time and illustrates this in terms of what it means in space, okay? So let's just give you some elements to do the demonstration. Where is the to do the demonstration in terms of harmonic function, and I will also remind you, I don't know if you remember how to write harmonic functions for E and B, so this will be a good opportunity to remind it. Okay. Okay, so harmonic functions. Okay, so the general way of writing harmonic function in electromagnetism is EM equal to E0. Here again, the underline means I'm implying this is a complex. This is a complex quantity, exponent of E K O M minus omega t. Okay, where E0 is equal to it's a 3-component vector, okay, and it's equal to E0x exponent of a phase along x, E0y exponent of phi y, and E0z exponent of a phi z. Okay, so this is the general expression for a harmonic plane progressive wave in electromagnetism. Okay, and again, it makes it very easy to do the demonstrations that we did, this, okay, because in complex notation everything is easy. Okay, so elements for the demonstration in the case of harmonic expression. Okay, so you'd have that deriving along dt is equivalent to doing what? To multiplying by what? By minus I omega, right? Minus I omega, right? And doing a gradient, okay, it's equivalent to doing dz, ez, okay? And this is equivalent to multiplying by what? By ik, you agree? Everybody's following? Okay, so this is like multiplying by ik. Okay, and then you'll do the same as before. You'll use that's the divergence of B. You'll use Maxwell. Okay, so divergence of B equal to 0, it would mean ik cross B equals 0. Okay, so K and B are orthogonal, and you write rot of E. Okay, so it's just, again, writing the Maxwell equation, and the divergence. Writing the Maxwell equation and taking advantage of the fact that everything is very straightforward in complex notation. So, by the way, here the fact that divergence of E equal to 0, this is only true in vacuum, and this is why E will only be orthogonal to K in vacuum. Okay? Only in vacuum. Okay? I actually do it because I've already done most of it. Okay, so you'll write that rot of E just like we did before, because it minus dt b. It means that grad of E, this is ik ez cross E is equal to 0. Okay? And this is also equal, this is equal to this, and this is also equal to I omega b. Okay? And so this gives you that B is equal to K cross E. Okay, which is also an important relation to remember. Okay, and from writing the other Maxwell equation, from writing rot of B, which is equal to 1 over c squared dt d, you'll get the same as before, minus 1 over c squared I omega E. Okay, and this is equal to I K cross B. The complex notation is really useful. This is the bottom line. Okay, and this will give you that E Z cross B is equal to 1 minus 1 C E, and this is what we wanted to show. Okay, this brings us to the same equality that we wanted to show before. Okay, so this is just another demonstration which is using the advantage of the complex notation for harmonic functions. Okay, so now I will quickly show you what all of this means in real space. Let's try and see if it works. יש פה איזשהו כבל, אני הבאתי אחד ליתר ביטחון.
לא הדוח?
כן, לא. To share my screen somehow, or it's already...
שהבית לא יודע, אבל
מישהו בבית? So I will post it on the Moodle so that... אוקיי, בינתיים המחשב שלי נקבע. טוב, תראו לי כמה, זה נראה לי לפעמים נכתק שם כדומה של משהו.
לא רוצה.
If it doesn't work in 2 minutes, I'll just post this video on the Moodle.
לא, הוא עובד, אנחנו שומעים שלוחצת. הוא לא מחובר.
כן, הוא לא מחובר, אבל גם פה הוא לא... Okay. Okay, so this is the relations that we derived can be summarized by this. Show it again. Okay, so I think the blue one, the red is E, the blue is B. And זה משנה בגלל שאמרנו שזה direct trihedron, כאילו שזה right hand rule orientation.
לא, אבל אם זה E וזה B, זה משנה או שזה B וזה E?
כן, אם זה הולך לשם, אז זה אומר לנו מי זה E ומי זה B, בגלל שיש את ה-right hand rule, אתה מבין? Okay, one last time.
B לשם וכן.
So, okay, and the last relation we derive is linking, so So the first part of what we said is giving us the direction, the mutual direction. And the last thing we talked about, which is the link between the value of E and B, is linking us at every time and every point in space, the norm, the length of the red vector and the blue vector. Okay, makes sense? One last time. Okay. With a nice title in French. Okay, so, על מה ללחוץ עכשיו? פשוט לכבות?
כן.
סבבה. Okay, so in the last 10 minutes, what we will do, we will derive one more thing from the Maxwell equation, which is the continuity equation. And the reason I care, I think you know already the continuity equation, but the reason I care is that you heard about the pointing vector, right? Yes. Yes. And what we will show now is an interpretation of the pointing vector instead of just giving you the expression of the pointing vector and telling you that you need to believe me that this describes the travel of energy in the direction of propagation. I will try to show it to you from the continuity equation. Okay, so this is 5. Continuity equation. Okay, so let's first talk about it within the context of conservation of something. Okay, and here specifically we'll approach it from the point of view of conservation of the charges. Okay, so charges conservation. Okay, so if I have a given volume and I'm counting the charges in it, okay, I can write that Q at T plus dt minus Q at T is equal to the volume integral of dt rho, this is the volume density of charges, dt d tau. Okay, and this is also equal by definition of J to J ds, right? This is a ds that is oriented according to like what is entering. Okay. Okay, so this will be equal to minus the normal dsx that you are used to. Okay, and from this we derive that dt rho plus divergence of J using the divergence theorem here, that this is 0 and this is just the continuity equation that you all know and you're used to. Okay? Now, one thing I want to show you is that again, as part of my advocating of the Maxwell equation as the source of everything, is that you could have reached this conservation equation from the Maxwell equations too. So let's do it. I know that Roth...
It's a little bit circular proof.
It's not a circular proof.
They are designed to apply that rule. That rule actually comes from Reynolds theorem.
I will say something about it in a second. Okay, if I use this Maxwell equation and I'm taking the div of this, okay, I'm getting the following: dt divergence of E plus mu 0 divergence of J. Okay, and this is equal to mu 0 epsilon 0 dt rho epsilon 0. Okay, because of this, because of the Gauss-Maxwell equation, plus mu 0 divergence of j, and this is equal to 0. Okay, and this is what I wanted to show. Okay, that dt rho plus divergence of j is equal to 0. Now, what Yarden is saying, and he's right, is that in a way what he's saying is that this was to be expected. Okay, we should not be surprised, and it's not some magic that this comes from the Maxwell equation. And the real reason for this is that if you remember, the Maxwell equations are linking fields, and so some of the Maxwell equations are linking the fields between them. Okay, for example, rot of E equal to minus d tilde B. This is linking fields, but some of the Maxwell equations are linking the fields and the sources. Okay, so it is indeed to be expected that the moment I'm talking about sources and describing behaviors of sources, this will contain anything about the conservation of these sources. Okay?
In introduction to electromagnetism, we just derived the Maxwell equation from this.
Yes. We're all super happy that everything holds in place. This is, I agree with
that's
it.
why I said it's circular, because we derived the Maxwell equation from
But
that
we
equation.
we didn't take this, and it's this plus Gauss-Maxwell plus Faraday-Maxwell.
No, what I'm saying that we derived the continuity equation in Introduction to Electromagnetism, and from that we derived the Maxwell equation, so it's circular. To say,
It's not
okay,
circular, it's rather than all these descriptions are equivalent. It's more this than circularity. But yes. Okay. So why did I remind you this? Also, I know that you know it already, because I want to use this as a way to interpret with you the pointing vector. Pointing vector. What is the time? I have 4 minutes. Okay, so I'll try to do it very quickly. Okay, so there is one thing that I will claim, and you'll have to believe me, okay, that I will not show. And this one thing is the following. I'm going to claim that if you have some particles, okay, the work these particles get, so you remember that sometimes in some of the continuity equations, I have another term here, the source term, right? You remember? Sometimes I also have a third term that is describing some injection of charges or anything that I want to describe.
Coefficient or something like that.
So, okay, so what I'm claiming, and you'll have to believe me, is that the rate at which, if I have some particles, okay, and there is some electromagnetic wave in the area where this particle exists, the rate at which work is done on charges, on all these charges, okay, dW over dt is equal to an integral of Ej d tau. Okay, this is the electric field, and this is something I'm not showing. Okay?
It comes from vector pointing interest, right?
No, I don't want. I want to do the opposite thing. Okay? What I'm trying to do.
To derive the vector pointing from that?
Yes, what I'm trying to do here, because I know you heard about the pointing vector and you know the definition, but what I'm trying to do is showing you what is the vector pointing without what it means without assuming that you know already the definition.
But you assume that we know that equation that we derive from vector pointing.
I'm assuming that you know what?
That equation, right?
This?
Yes.
No, this you don't know from vector pointing. This, if...
That's how we derive it.
No, this is not how you derive it. So I'll give you the very... I want to finish on time, but I'll give you some intuition for it. Okay, so the work here is equal to, for one particle, is QEdL. Okay? And if you have several charges, okay, J is rho V. Okay, so if I take the derivative of the work, this is not super rigorous, but this is in essence where it comes from. So this is dl over dt. Okay, and this is rho E did V over dt. And this is JE, and I didn't say the word pointing, and I didn't assume anything about pointing vector. Okay? Okay, and now okay, I'll do it very quickly to release you, but I will write the Maxwell equation. So we know that rho of B is equal to mu 0 J plus mu 0 epsilon 0 dTE, right? So I can rewrite EJ as the following: E rho of B divided by mu 0 minus epsilon 0 dTE. Okay, which is also, there is some calculus trick here, so this is also E rho of B divided by mu 0 minus dt of half of epsilon 0 E squared. Okay, and by using, so this is one equation I'm using, by using the fact that rho of E is minus dt B, okay, I can show something similar, and I will leave it to you as an exercise. Show that for every mt, the divergence of E cross B divided by mu 0 plus dt of half plus E dot G is equal to 0. Okay, this is a very important equation. You would recognize here the pointing vector, but the point here is that this equation is actually a conservation equation. Do you see this? Because I have a divergence term, I have divergence term plus a time derivative of something, and this should remind you this is the volume and energy density, electromagnetic energy density. You remember this? Okay, and this is a source term. This is where this interpretation. Okay, so this is just a conservation equation for what? What is rho here? It's the density of what? Energy. Okay? So I'll say a few words about it in the next lecture because I'm aware that I did it very quickly. But the idea, what I want to show you here is that this, which you know as the pointing vector, is actually some J function. Okay? It's describing the travel of some quantity, where this quantity is what? The energy. Okay? I could also have just remind you the definition of the pointing vector and told you it described the travel of energy. But here we didn't assume it. We just wrote the Maxwell equation. It led us to some conservation equation. Conservation of what? The energy. And within this context, the pointing vector is interpreted as the J describing the travel of energy. Okay, so I will repeat this in the next lecture, and we can finish here. Yeah, and I mean, regarding what we said in the beginning, if you also talk with other students about this attendancy thing, okay, I want to emphasize that if I'm teaching to 3 students and deciding not to teach, it's not a punishment or anything. It's just that's my interpretation of the fact that I'm teaching to 3 people, and I think it's a fair interpretation, is that it's not required. We don't need to teach in person, and recordings are enough, and there are amazing recordings from the 2 last year, and I can give them to you. So this is important for me that you understand. And it's not any kind of punishment. It's just תיאום ציפיות. And if it's not needed, it's not needed. And my effort to come is not needed. Okay? So. I really hope that there will be more than 10 people next time, because I enjoy this interaction, okay?
לי הסמסטר הזה, כל שאנשים מגיעים.
אני ממש מבינה, אבל אולי זה אומר שזה לא נצרך וזה בסדר גמור.